Thanks for having me back to EuroPython. I'm excited to deliver my first Bytecode talk. My previous talks covers Python parser and the type systems. So Bytecode feels a follow-up for me and hopefully for you too. Before that, I want to start my motivation. But before that, I want to take a kind of selfie. Have a smile here. So my last year talk was about typing console, PEP 729. And during the preparation, there was actually a news happening on Hacker News. It reports a famous company decide to impact the PyType and its maintainers. And PyType was a core part of this PEP, and also for typing console in a PEP doc you can find it. This makes me wonder, what's PyType's future, and can anyone easily maintain it as before? Well, at this point, you probably have a question on your mind now. Wait a minute. How is type checker and bytecode connected each other? I'll get there, but let's talk about what bytecode is first. And many of you may already know bytecode well, but for those who don't or need a refresher, here's a bytecode 101. In this example, we have a one-line Python code, x equal to 1 as an assignment. And we can use this module to disassemble it into bytecode. So the output will be something like this. We call it bytecode operations. Without this module, in fact, you can still use a compile built-in function to generate code object. And with the code object, you can find the code property under it, and then you can further use this module's OP name to map those bytecode into the human readable name. So the thing is, like, how does the Python compile the Python code into the bytecode? This part is still unclear. The first step is a thing called lexer and parser step. So Python code firstly goes through it and convert to the thing called abstract syntax tree AST. And this step can be reproduced by AST module. So you can see, like, for example, the x equal to 1 assignment. The AST will look like a tree like this, a root module, and an assignment node with two leaves, or target x, and the value constant 1. And later, after we get AST, the compiler transforms the AST into the bytecode. And the bytecode, you can see the connection between the AST and the bytecode will be like, we have the load const bytecode grabs the const 1, and the store name assigns the const 1 into the variable x. And there's assignment tied to the stack operation. And since x equal to 1, x assign 1 to x is so simple, so the return is just none in this case. So we understand, like, how the Python code is compiled to bytecode. The next step is, why do we need to do so? This may be an open question. One answer I like refers to the modern compiler architecture. Modern compilers split into front-end compiler and back-end compiler. And source code firstly transforms to a thing called intermediate representation, IR. And then the IR transforms to the machine code. So look at this, and then look at another one, the CPython's design. You'll find a kind of similar properties. We actually convert the Python code firstly into the AST, that could be considered as IR, and later we convert the AST into the bytecode. So we still haven't yet answered why compiler is designed this way. There are three benefits behind this, at least what I know. First of all, the platform support. So obviously, that's probably the most important one. Bytecode is a platform-independent representation. So what we care about the environment is the VM. We need to have a dedicated virtual machine handles the complexity for the platform. But for people who generate bytecode or anything before that, they can focus more on the bytecode itself, or the rest of the part don't need to care about the environment complexity. The second benefit is IR flexibility. This can be less obvious. For example, there's one example is like, imagine you have a JavaScript code, and you can convert this JavaScript code into the AST in Python. And technically, you can run this JavaScript code in Python's VM because that AST can later be converted to the bytecode. That's probably something called transpiler. And there could be some more use case behind this kind of IR flexibility. The third benefit is optimization clarity. So optimization can be at both AST and bytecode levels. For example, in AST level, numeric operation like power can be optimized during optimization. In this case, you can see like we have the power operation here, and when we do the optimization setup in AST, it generates another kind of tree like it's already optimized. For the bytecode, we also have the certain optimization. In this case, it's unreachable code. So in this function, intentionally just put something that is never be able to reach by any runtime logic. And in this case, because during the time we generated the bytecode, it actually can detect like, okay, this code is never be able to be executed through the virtual machine. So you will see just like the code is just discarded when the bytecode is generated. So we have covered how and why we need bytecode quickly. So let's talk about the C Python's bytecode development. Perhaps like the first thing, at least for me, the first question I have is Python is a really mature product. I mean, the open source there. Then do we still need to introduce a new bytecode for it today? Yes, absolutely. You can find in each Python release page, we have like Python 3.13, we have a little bit new bytecode change, and the Python 3.12, there are a lot. So today, I want to just pick one of them in Python 3.12, PEP 709, to introduce what sort of bytecode change happened in CPython. In case you are interested why I picked this, the reason is because it's new and comprehensive. It's new enough, I believe, 3.12 is still very new. And comprehensive is just the document actually provides a pretty comprehensive content. Plus, it's a single new bytecode mapped to one PEP. That's a very clear one new bytecode example that we can refer to. And the title of PEP 709 code inline comprehensions. And it provides an example here. The impact code is like they define a function and argument is a list, and then we run just a list comprehension inside the function and we return it. The goal for PEP 709 is to improve the Python performance by simplifying the bytecode behind the Python code. So to know that, we need to basically go through all the bytecode together. The bytecode generated before PEP 709 looks like this. You'll find out like the make function is performed for list comprehension. And that's actually pretty surprising, especially if you are just a Python developer. You wouldn't expect you define a function, but the bytecode actually generates another function for you. And so we need to trace it line by line to understand why the make function is here. Assuming you run it with a stack-based virtual machine, you will see the first bytecode resume happen, and it initializes the friend and the metadata. And so we have basically set up in the well, left-hand side. Oh, I think yours right-hand side. Okay. And the second bytecode localconst puts the list comp function call object to a stack, and then we have a callconst that holds it in the environment. And the make function here creates a list comp function, so the definition is not listed here, but we'll enter it later, not at this point. And loadfast loads the list argument to the stack. And we have a local variable holds it as well. And getIter prepare the list to the stack for iteration. And so at this point, we can call the function, enter the list comp list function object. And there's one key thing happen is like there's no argument passed to this function. So the list of this top side, the function f's list argument is actually passed implicitly. And it passed implicitly in this ways. We are now in a function, another function. We need to resume it as well to set up the friend and metadata. By the time you will see, there's actually a callvar name, the local variable there, actually holds the variable from the caller function. And with that, we can continue to do the list comprehension. So our step is like we build a list, just have an empty list in the stack inside that function. And we load the iterator we got from the caller, and then we can start to operate it. And in this case, it's pretty simple. Just we start to for iter it, and we do nothing. We just loop it and get the value, and do nothing and just store it back to list. So in this case, just the store fast stores the iterated value, and then covariance local variable holds it temporarily, and load fast immediately loads that stored value back onto the stack. And that's exactly what this function does. And list append just, OK, finally we finish the loop and we put it back. And jump backward just again, if there's still something in the list, we just do it till the end of the iterator. And then end for just stop the iteration, and the list comp result is now on the stack here. And then we return the value, just return a list. Back to a caller, the call function right now got also the return the list, and we can finally return it as the list function defined. PEP 709 here drops the make function by a new bytecode called load fast and clear. So we need to trace like how it drops this make function step and use another approach to solve the same problem. So I'll just also, again, quickly go through the bytecode to see what's going on. Like before, we have resume set up the friend, and we have load fast to load argument, and we have the get iter to prepare the argument to start the iteration. This part is the same, but the next step is different. Next step, we don't use the make function anymore, but we use a thing called load fast and clear. This load fast and clear basically does the thing is try to load the friend local variables into the covariance. And then we do the swap. In fact, you can see many swap in this bytecode. And we'll explain that one by one later. But basically, the swap is trying to manipulate this stack we have in the virtual machine to eventually make the virtual machine pretty similar to the previous with the make functions stack in that function. So we can operate the same for loop. And so the first swap performs, and the local variable is stored, and the iterator is on the top now. So you can see there's actually, before it's like a local variable is on top of the stack. Now we push it down, and so we basically can touch the iterator rather than local variable now, and we kind of hide it somewhere. And next step is we can build a list. So we have an empty list there, and we need to swap it again to make it the shape closer enough to the previous make function status. And next time you can see, it's like we actually get the top of the stack. It actually contains the same results we need for running the iteration. And with this, we actually don't need this comprehension to make a function, but we can just run the for loop as previously the make function does. So we can skip that part. Imagine like we already finished all the loop. And at the end of iteration, the result on top of stack will just be something like this. And we finish the loop now. And then we can swap back the local values to the top and store it back to a covariance. So you can use that. So imagine like a list function, if there's something happened before the list comprehension or after list comprehension, then you can still continue to do the thing you are doing. And so let's recap, just final recap here is paper 709 does the thing is like no more make function needed. We can still achieve the list comprehensions. And the performance gain is clear. You can see like we don't need make function, implies like we don't need to initialize the frame. And it also shows a kind of obvious the human visible the bytecode number difference. The bytecode is smaller with the list change. And of course, like a swap is some very simple operation, so you can also imagine like the performance can get some improvement after that. I don't know about any of you, like after going through this path, what's your feeling? But to me, my question is very, very, very simple. This looks very promising, but why this is done in Python 3.12, not 3.11 or before? This should be something like we can do already. Okay, so I hope this meme explains this well. I think basically, I mean, we touch a software we know, like if things works, then just don't touch it. And it's just so complicated, and that's why nobody touches it. So actually, I mean, the true takeaway here is bytecode is very difficult. It requires a deep CPython understanding, and it also requires the understanding of the change impact to other project and even the CPython itself. So we can move on to the bytecode manipulation now. Back to the initial question you may have is, how come the type checker and bytecode is related? Okay, so in fact, if you try to merge bytecode and type checker, you'll get a thing called PyType. That's the thing I mentioned earlier. PyType used the bytecode-based type inference to check the untyped code. Back to the time the type annotation was introduced, the Python codes aren't type annotated that much. So this idea was introduced at that time to check those Python code that is untyped. And the fact is, like, it looks something pretty promising, but if you look at all the type checkers today, I mean, even the modern one, the TY, the Firefly, they are all ASD-based type checker. None of them is bytecode-based type checker. So what's the difference behind that? You can maybe give you some time to think about this question. Consider these three cases. So all three causes the type error in runtime. The first one is a wrong argument type to a function. The second one is wrong argument type, but to an inner function. And plus, the outer function has no type annotation. And the third one is same as the second one, but the outer function has type annotation. So which one AS-based type checker cannot check? Okay, I hope you have time to think. Hopefully you get this right. AST-based type checker cannot handle case 2. Of course, like you can say, it technically can still to do it if you try to static analyze it through all the code under the logic, like before calling the inner function. But AST-based type checker usually don't do so because it's too complicated and it's not the thing they are good at. And instead, bytecode-based type checker can handle these. And so, hey, but if bytecode-based type checker can handle something like AST type checker can't, then why people choose the AST one instead of bytecode one? Well, the answer to me is simple. The maintenance burden. If you try to develop something based on the bytecode, you will need to follow CPython's bytecode change plus CPython type annotation change. And of course, like you also need to implement your own virtual machine to handle exactly the same thing, to handle the bytecode, and plus also have your static analyzer to handle the type annotation. So that's just additional burden for the maintenance, and you need to follow the CPython very closely. Secondly is performance reason. It technically can be powerful, but often very slow if you try to handle some very crazy case, like you need to generate the bytecode in the very deep level. I do have more example in my fourth deck. If you scan the QR code, you can find the more examples there. So one thing further to say is like a PEP 09 we just mentioned. In fact, PyType, they need to implement this bytecode, exactly bytecode, into their open source solution, and they need to implement that in the VM, and also implement the way the VM handles that, and follow the CPython's way to handle the same. And so it's kind of getting super complicated. There are also more other examples other than PyType does the same. The tools like a Python XDs or VM required solution like a EuroPython, PyPy, also has a corresponding bytecode manipulation implementation there. And they will need to handle the CPython bytecode changes, of course. And clearly, at the time when I prepared the slide, you'll see like the version they support the CPython is very, very delayed. Like at the time, the EuroPython has an issue talk about support Python 3.12, and now it's already 3.13. It's going to be 3.14. And PyPy, not to mention, is just 3.11 at the time. So the support is very slow, and because they need to follow it much more than other tools. So I mean, second takeaway here, it's another meme I try to say. Bytecode is here, and the Python project is there. So modified bytecode, manipulated bytecode is very, very expensive. It requires developers' patience to see Python itself, and how to keep updated to the newest CPython version. And plus, it's hard to connect. That's probably another thing I want to say. Hard to connect the business value directly in the reality. And so, the last part I want to say is the bytecode and the community part. Back to EuroPython 2013, Larry Hastings said there's no good reason for anyone to study bytecode unless you are a core developer. I think that's still true today, except because the community grows and we have a lot of Python population and ecosystems. So developers who try to manipulate bytecode like PyPy, like EuroPython, or like PyType people, they need to study bytecode. It's actually a thing, additional thing happened, I think, after 2013. And so there are tons of ways, of course, for us to deepen our understanding to latest the CPython bytecode. Paper 709 as an example. It has a discussion thread, talk about its impact to other tools. And also the PEP itself also talk about impact to other tools. And we have conference like EuroPython here. So we always have many stages. People can interchange opinions for especially ongoing efforts. And we also have core developers run the podcast, run the YouTube, and also write bloggers, especially talk about the detailed context behind the change, ongoing change, existing change, and so on. So in a word, community engagement transforms today's Python into tomorrow's Python. With patience, everyone can be part of them. I have one last thought here. I don't put any text here, but just what I want to say. In recent 2 years, I found out there are many tough decisions happen in a lot of companies, like the motivation I mentioned. Those companies' community trust will easily be impacted with just an announcement. Meanwhile, we are experiencing a Gen AI hype. So this makes the resource funding harder for the folks who has patience for the CPython. And so what I want to say is like you happen to listen here or remotely or in a YouTube in the future, you are really passionate about Python, and that's something I want to say thank you. Your passion in Python is truly priceless. Yeah.
Yeah, thank you very much, Kir, for this wonderful talk. Very, very well done. We have time for a Q&A again, and for those of you who want to ask questions, which would be great, please come to the microphone. As I said, we put it there because otherwise it would be in the way of the camera. Anybody? People coming. Yeah, go ahead.
Hi, thank you for the talk. Just one thing to clarify, GraalPy doesn't use CPython bytecode at all because it would be too hard to keep up with CPython. And
okay.
We also want to have our own bytecode to optimize it in different ways and so on. So that brings me to a note or maybe a suggestion, brainstorming idea. I see that it's easier to statically analyze bytecode rather than AST. But the CPython bytecode is changing all the time, and there are good reasons for that. If that is so important for certain communities within Python, would it make sense to define some sort of like a stable bytecode that you would use for static analysis and things like that, and so that you can keep CPython evaluating its own bytecode and have your other bytecode that's easy to analyze?
I think I would say it depends on the project's background, but at today's economic atmosphere, I really feel like you need to have a really strong reason to justify the project that really need to manipulate bytecode, particularly because, for example, the PyType, historically it used bytecode because we have, I think maintainers, they are very close to the CPython core dev. Even some of them may be just the CPython core dev. So for them, it's like not so hard to follow up the CPython's change. But given the new atmosphere of economics, in some cases, if a new developer joins, they are not interested in CPython's bytecode. It's going to be very hard for them to really follow up the new change, and because the consequences, like it's getting very hard to maintain that. So yeah, I would say just like again, just business reason should be considered when thinking about this kind of innovation.
Hey, thanks for the great talk. So maybe I will add to the reasons why you may study bytecode. I think it makes sense to study it when you want to benchmark something, because nowadays when we have this specialized bytecode and people do benchmarking of Python code, they may do it incorrectly because they don't understand what's going on under the hood when the specialized bytecode kicks in. But I've got also a question. Does it really make sense to put all this effort into like doing some kind of bytecode level type checking versus doing it just in runtime? You know, not statically, but just do it in runtime. Because, well, if you do it in runtime, you do it like.
Okay, that's a type checking question. Firstly, is the runtime type check is another thing. That's not today. We talk about type annotation in the Python world. We talk about static type checker is needed, but bytecode-based static type checker. Basically, everyone agrees at today's Python code setup, it's probably too overwhelming and not needed. So it's definitely not really a good idea to do in that way. Of course, you can see the academic value behind that, but other than that, I would say the practical value will be pretty limited because you can see, like, I mean, as I put this here, just all the. Basically, I mean, typing console people develop these things
well,
here.
you mean it maybe because nobody did it first? Like it was easier to do AST-based, right?
It's for historical reason. Like I think bytecode-based decision for PyType was fully this historical reason, and the current status it doesn't make sense. In fact, so definitely for as I say, like academically it could have value because you can do some very interesting type check.
I mean, if it provides value compared to AST, you can just put it in your CI/CD and have more type checking, right?
Oh, sorry, can you repeat again?
I'm saying that if PyType is providing more value than the AST-based solutions, we can just put it in CI/CD and have a better type checking, right?
But maintaining it is expensive.
Yeah.
Yeah. That's a different thing.
I mean, if it works.
Yes.
Yeah, thank you.
Thank you.
Okay, we would have time for more questions, and yeah, this is probably the opportunity. No time like now.
Yeah, I have one more question. So, because we saw this new bytecode introduced, and it seemed like maybe there are some other use cases for it, but we had this swap instruction afterwards. Why the swap is not included in the bytecode? If you know that. Why
the swap is what?
So if you go to the slide that you have with the new bytecode instruction, I don't know if it's it's there, right? There's this load fast and clear, and there is a swap.
Yes.
Is there a reason not to include the swap inside of load fast and clear? Because it's like from what we have seen here, it seems like maybe the swap could be included here. Build list definitely not, because you may have an iterator being built here instead of a list. But swap seems to be something that you may want here, but maybe there are some other use cases where it's not really needed. I guess that would be something to look up in the PEP, because maybe there are some other use cases for it.
I don't really know the answer. I need to dive deep into this, but probably my guess will be that will make it not generic enough for some cases, and that's something. Again, I need to check the detail. Yeah, or maybe someone here knows the answer.
Okay, thank you.
Detailed suggestions here.
Yeah.
Well, that's good, right? It's about getting the crosstalk started and fostering it. Any last-minute question here? We have 1 more minute. All right, you're all hungry, wanting to get lunch. Okay. Well then, please give another thank you round of applause to Speaker Kir.